So in this problem, we've got some probability distributions of things, and it gives us a problem. And so it's pretty straightforward. I'm not going to read it, but essentially what we're doing is we're just taking, we have advisor suggestion, pre-professional. These are independent, so I can just use my multiplication rule to get 0.035. So that's how we get B. The reason the answer is not B is that it's saying, what's the probability that a college student in general decides to change a major based on advisor suggestion to pre-professional? So there's one other thing going on, and that's that only 3/4 of college students change their major. So we need to multiply this 0.035 times 0.75. I overlooked it myself, so I was trying to figure out why is it not 0.035, and then I overlooked that 3/4. So there it is. So the correct answer is actually A. And so hopefully this is just a reminder of, like, make sure you're reading the problem twice. Make sure you read it over, make sure you're catching all the little pieces of information thrown in, because we think of these kind of upper areas right here as just kind of like just giving us some context, but sometimes they're providing important information. Okay, so that is probably good enough on that. Okay, so we've got these things we still need to talk about. We're probably going to skip over Bayes' theorem quite a bit, but I'm going to talk about it just in the smallest way because it's amazing and we just don't talk about it in this class. So replacement, this is a very straightforward idea, and I'm going to zoom through this one because I realize we need to save more time for other parts of class. So we have the idea of using replacement. We've been doing it. So if you pull the ball from a bag of 10 as a component in a trial, so regardless of what you pulled from the bag, the probability for drawing the second ball is going to change depending on whether or not you put that first ball back into the bag. So if the first ball is red and you put it back in the bag, the probability of the second ball being red is unchanged. These events are independent. If you keep replacing the ball, then it's the same trial over and over again, the same component over and over again. Now, if you took a ball out and you kept it out, then your probabilities are changing, and we can see that these are not independent events. The probability of the second depends on what you draw out the first time. So when you hear replacement, with or without replacement, then that is going to change how you approach the problem. Any problem that has replacement will consist of independent events, and you can just use your regular multiplication rule. It'll most likely be the multiplication rule that'll matter. Any problem that involves components without replacement will result in events that are not independent, and you're going to have to use the conditional probability found in the general multiplication rule. So we've got a couple of scenarios. Again, I want to do this fast. So I apologize if I go through stuff too fast, but that's so I can hopefully slow down on some of the more complicated stuff later. So cards are drawn with replacement. And this is the scenario. The cards are drawn with replacement. We put it back in. So every single time we draw, we have every card has equal probability of being drawn, all 52. So we're going to try and draw a heart. So it's going to be the probability of a heart and a spade and a club and a red card. And now I can just figure out the probabilities of those things. Because it's all and, it's the multiplication rule, I'm just going to multiply them together. So the probability of a heart, well, that's 1 in 4. The probability of a spade, that's 1 in 4. Club is the same. And the probability of a red card, well, there's half of the cards are red, so that's 0.5. So now I can just multiply that out. It's the multiplication rule. And I got 0.0078. All right, not likely to happen, but there's a chance, I guess. The other scenario we have here is that the cards are drawn without replacement. So now, if I'm going to write this out in probabilities, then it's going to be, the first card I'm going to draw is the probability of getting a heart. And I have a full deck, so I still have the same probability. So I'm going to, the probability of getting a heart. And the probability of getting a spade, but now it's a probability of getting a spade on the condition that a heart was drawn. And it's the probability of getting a club on condition that a spade and a heart were drawn. And the probability of getting a red card on the condition that a club, spade, and heart were drawn. And these are now conditional probabilities. I can't just use the same numbers as before. Well, except that I can for the first one. It's a 1 in 4 probability the first time around. What's the probability of getting a spade for the second card if I don't replace? And you don't have to tell me the decimal, you can tell me a fraction.
(13/51).
That's it. 13 spades are still in the deck, but I only have 51 cards in the deck. Okay, what's the probability of getting a club on condition that a spade and a heart were drawn?
13/50.
You got it. I hope. Were you eating? Does it taste good? I don't know. That's what it sounded like.
Yeah, my chicken tender.
Ooh. Dang.
Delicious.
Yeah. Sounds it. I can kind of smell it a bit. All right. So now we've got the probability of getting a red card on condition that a club, spade, and heart were drawn. Well, we can start with the easy part. How many cards are still in the deck?
49.
49. Now, on the condition that all these things happened, a heart, then a spade, then a club were drawn, how many red cards are still in the deck?
Would it be 25?
You got it. So one heart was removed, but besides that, we still got 25 of them. Now, this does not change things very much. You'll see when we do this, but these are now the new probabilities for this to happen. So we can do this. All right, and that might take you a little bit longer to type those in. You know, that really helped us out because we went up 0.06% in our probability here. So, yeah. And well, but intuitively that should make sense. So your probability goes up because you have, not in every case. Sometimes your probability goes down when you don't have replacement. But in this particular scenario, it kind of makes sense. There's fewer opportunities for failure when you're drawing in this particular way without replacement. Okay, let's move on. There's not a whole lot to this idea, but just remember you have to do conditional when you don't have replacement. Okay, this is, these are some slides that we had from from Friday. Sorry, that's what I was trying to say. So these are just slides that I'm recycling because we introduced this idea of the general multiplication rule that says that we replace the probability of B from the multiplication rule to the probability of B given A. a conditional probability. And now this is all for the sake of independence, and we're going to see how this all ties together. The general multiplication rule can be used in any situation. So here are some independent variables. We're going to be looking into how to determine if they're independent variables in just a second. But, well, actually, we're doing that right here. Are we? No, okay, so this is the other part. So notice that the probability of B, which in this case was preferring in person, was 20 out of 50. So that's 0.4. The probability of B given A, well, A is that event senior. So on the condition that it's a senior, it's 16 out of 40. And those are both 0.4. They're the same. So it doesn't matter whether we use the general multiplication rule or the multiplication rule. Okay, and this kind of leads us into determining independence. So let's look at this one real quick. This table, I told you from the beginning that these are independent, but now we're going to kind of see why that is. So the good thing about independent variables, independent events, is that we can check it lots of different ways. So I'm going to check this for independence twice, maybe even 3 or 4 times. So I'm going to start off with this condition. Well, no, that's the one we already did. So let's kind of switch it up a bit. I want to check the probability of being a junior. Okay, so that's going to be 10 out of 50. So the probability of being a junior is 10 out of 50 or 0.2. This is going back to chapter 3 stuff, so hopefully this is also going to ring a bell a bit. But now I want to find the probability of being a junior on condition that you prefer remote. So I'll put R for remote. Okay, so on condition that you prefer remote, there's a 6 out of 30 chance that you're a junior. Well, look at that, that's 0.2. Maybe I changed my condition. Maybe it's the probability of being, the probability of being a junior on condition of preferring in person. Well, here's that condition, and now it's 4 out of 20. And that gives me 0.2. So notice that all of these probabilities are the same. If all the probabilities are the same or approximately the same, and when I say approximately the same, like within 1% of each other, 2%, maybe 3% at the extreme. So if they're close enough, and there are other ways of determining close enough later on. But anyways, for now, these are obviously independent because it doesn't matter what a person prefers for their school. There's a independent breakdown, and you're going to have 20% of juniors supporting either, and 20% of juniors overall. All right, we can check this different ways. If these are truly independent, then all of these will be the same too. So now we'll go with prefer remote if you're a senior. So prefer remote given that you're a senior. And then just the preferring remote overall. Let's compare those two. So that's 24 out of 40, which is 0.6. And then there's 30 out of 50 for overall, which is 0.6. So we can see there's independence across rows, or down columns. So it doesn't really matter how you're looking at it, but we want to kind of use this idea. And this was messing up earlier on me. Let's see if it fixed itself. Yeah. We'll just go with this. Okay, that's okay. Basically, all this is saying is that independence can be defined as when the probability of B given A is the same as the probability of B, then you have independence. And in our previous example, that was maybe the probability of preferring remote given that you're a senior is the same as the overall probability that people prefer remote. So there you go. That idea is not overall that complicated. It is a review of stuff we talked about in third chapter, but it is an important concept to keep in mind. All right, so now we can go through, do I want to do this one? You know, I think this gets the point across. We'll just kind of shorten this up a little bit. So we have a situation where we need to create a two-way table. Now we're going to be learning today the difference between setting up a tree diagram versus setting up a two-way table, and the prompt looks similar. So I'll point this out right now, and then I'm going to come back to it and probably repeat this information. But in this, 995 adults were surveyed. 81.5 of them, 81.5% were over 30. So this gives me the probability of event A. And I might change what I call that, but for now, right now, let's say that's the probability of event A. In that study, the National Sleep Foundation reported that 36.8% of all adults snored. So this is the probability of event B. These are those marginal distributions that I'm going to put in my two-way table. The last thing they tell me is that 32% of the respondents were snorers over the age of 30. So this is the probability of A and B. It's going to be some kind of an and. It's not always A and B. It could be A and not B or something like that. Or A and, yeah, you get the idea. So this is the kind of information I'm given. Probability of A, probability of B, probability of A and B. So now I want to go through and answer this. I want to create a two-way table, that is. So first of all, I'll put 30 up here, and I have two possibilities. You're either over 30 or under. I guess you could be right at 30, but we'll just say over 30 and under 30. I'll use a plus and the minus here. You might find that useful notation. You have, what's the other one? Snoring or not? Yeah, so yes to snoring or no to snoring. So they gave us the overall probabilities for the margins. So 81.5% of the respondents were over 30, which means 0.185 were under. And snoring. So that's the overall probability of that. And that means 0.632 did not snore. All right, this should add up to 100%. All right, I'm just filling in the table. So I'm going to go ahead and put this 0.32 right here because that's the probability of A and B. Yes, they snore. Yes, they're over 30 years old. And I'm going to let you guys fill in the rest of this table. All right, good. All right, we got one more to fill in. Thank you for filling those in. And I believe that's correct. Okay, so we've got our table filled in. Remember, this is just addition across the rows, down the columns, doing some really basic algebra to figure out what's missing. Okay, so we've got this. And now the first question, what percent of the respondents were under 30 and did not snore? Go ahead, someone circle the answer to that. There it is. About 14% met those criteria. And the fact that these are, what's the word I'm looking for? These right here all add up to the 100% right here. So the margins have to add up to 100%, each of them. But then this conditional breakdown in the middle has to add up to 100% total. So I already know that whatever relative frequency I get in that table is the overall probability of that from the population. If they're asking for a conditional one, then I'd have to consider it out of that condition. All right, hopefully you're clear enough on all that fun stuff. So is this independent of age? Is snoring independent of age? And we can check this by column. We can check this by rows. It doesn't really matter. So let's just kind of go through this one real quick. If I look at this and this, what I'm really saying is that the probability of being over 30 has to be the same as the probability of being over 30 on condition that you snore. And that's 0.815 for the probability of being over 30. So now it's just got to be the conditional probability of 0.32 out of 0.368. And I know you guys, I would like to be able to just kind of turn this over and let you guys solve it, but I am trying to do things a little fast, I guess. So this is 0.8696. So now the question, is this close enough where I can consider them independent? The overall proportion and probability is 0.815, but the conditional probability is 0.8696. And I would say this is far enough away that they are not independent. You get into some tricky areas, like let's say this was closer to like 0.825. I don't know what the number could be. But let's say it's 0.825 and 0.815. It's like, that's where it's close enough, I'd say, you know, maybe they are independent. It's never going to be exactly the same proportion, the exact same probability. But if it's close enough like this one is, then maybe you say they're independent. This right here, I think it's safe to say those are not equal. These are not independent. And remember, you could have gone down the columns rather than across the rows. It would have to be independent everywhere. Okay. Any questions on independence? All right. There's just a little bit more dealing with this. Oops. Right here. Okay. We are not going to go over this completely right now. We are going to look at this one in a little bit. But the first part of this, just asking, are these independent? Or explain how these statistics indicate that it's not independent. So it's telling us, but we need to know why that's the case. So suppose 23% of adults smoke cigarettes. It's known that 57% of smokers and 13% of non-smokers develop certain lung conditions by age 60. So what they're giving us is the probability, move that over here. So the probability of having a disease, so I'll just say disease, given that you're a smoker, is 0.57. The probability of getting a disease given that you're a non-smoker is 0.13. If these were independent, then these two probabilities should be the same. And quite clearly they're not. So that tells us right there, we don't have to do anything else, that these two conditional probabilities are not equal, so these are not independent. And we're going to come back to this problem because there's more to this. In fact, we're going to come to it very soon. We're looking at tree diagrams. And kind of the key thing, is it raining? I think it might be raining over here. meaning I hear like 3 raindrops. Sorry, I'll get back to this. Sometimes the easiest way of diagramming is using tree diagrams. Now, it's kind of tough to know when to use a tree diagram, when to use a two-way table. And that's why I wanted to draw this distinction from the previous problems. A recent Maryland highway study found that in 77% of all accidents, the driver was wearing a seatbelt. Accident reports indicated that 92% of those drivers escaped serious injury, but only 63% of the non-belted drivers were so fortunate. So I want you to see what was given. I'm going to come back to this one because I'm going to go back in time to this one right here. And we've got the probability of A, the probability of B, and the probability of A and B right here. Those are the 3 pieces of information we were given, and we decided this is a great opportunity to set up a two-way table. Now I'm going to compare that to this other problem. And this requires close reading, but 77% of all accidents had a driver wearing a seatbelt. Well, okay, so that's an event, wearing a seatbelt. So that's a probability of, I'll say A for now. I'm going to give it other titles later. So that's kind of one of my marginal probabilities. But now let's look at this. Accident reports indicated that 92% of those drivers escaped serious injury. Those drivers meaning the ones who were wearing a seat belt. This is conditional. This is the probability of B given A. The probability of being uninjured, more or less, given that you're wearing a seat belt. Only 63% of the time, the non-belted drivers were so fortunate. This is the probability of being okay given the condition that you were not wearing a seatbelt, the complement of A. So what I have instead of A, B, and the probability of A and B, now I've got the 2 conditional probabilities and one of my marginal probabilities. So in this case, if you're reading it carefully enough and you can identify that you've got conditional probabilities, this is where you probably want to do a tree diagram. I should add, you can create a two-way table, and if you can think through it clearly enough, you can actually figure out the two-way table from here. But it requires a little bit more kind of holding on to a lot of information in your head at the same time. So I'm not going to go through how you might do that. The tree diagram is pretty straightforward. In fact, it's already done, so I'm not going to spend too long with it. So the probability of wearing a seatbelt is 0.77, so we know the probability of not wearing a seatbelt is the complement. Probability of being okay given that you're wearing a seatbelt, that's given. And it was 0.92, so the complement of that being injured is 0.08. And the last one right here, there's a typo. The probability of being okay given that you're not wearing a seatbelt is, well, it just went out of the way, but 0.63, so the complement of that is 0.37. Okay, so now we can go through, and we're going to create this in a second, so I'm not going to spend too much time, but when you create these branches for your tree, you're going to add the probabilities onto those branches, and then later we can just use our general multiplication rule down the tree, down the branches. So like here, I'm going to multiply 0.77 by 0.08. This is a typo. That's supposed to be 0 right there. 0.77 times 0.08 gives me the probability of both of these because it's a probability of A and the probability of B given A. So I'm just multiplying. So that's kind of how this all comes together. And we'll call that good for now, because now let's go to a new situation. And if you want to see this, this is on page 365 in your book. It's problem number 44. It's going to be up on the screen, but if you want to kind of see it for yourself, there you go. A company manufacturing electronic components for home entertainment systems buys electrical connectors from 3 suppliers. the company prefers to use supplier A because only 1% of those connectors prove to be defective. But supplier A can only deliver 70% of the connectors needed. The company must also purchase connectors from the other two suppliers, 20% from supplier B and the rest from supplier C. The rates of defected connectors from B and C are 2 and 4 respectively, 2 and 4%. You buy one of these components, and when you try and use it, you find that the connector is defective. What's the probability that your component came from supplier A? That's a lot of reading, a lot of processing, but if we look at it, we can see that we've got some conditional probabilities. All right, so we've got, let's see, if we look at this, maybe we could start by diagramming a little bit. I'm gonna be careful how I do this so I don't go too far. So I need to get a supplier. And my first supplier, or A, B, and C are the 3 options. I get 70%, I don't need the 0, so 70% come from A, 20% from B, and that means 10% from C. Okay, now the conditional part is that 1% chance of failure on the condition that it was bought from supplier A. So 1% chance of failure, and then that, sorry, that's 1%, 10%. So that means I've got a 99% chance of success. So you could use W for working or whatever you want. So, and I can maybe even write this failure on condition that it's from A, success on the condition that it's from A. All right, now we can just go down the line this way. So B, there was a 2% chance of 0.02, 0.98, 0.04 from C, so 0.96. And it's going to be failure on condition of B, success on condition of B, failure on condition of C, success on condition of C. So really I can just multiply this out. I might not write these for all of them, but this is just A, well, let me do it this way. It's the probability of A and failure on condition of being A. So this one would be the probability of A and success on the condition of being A, which is really just multiplying down the line. 0.7 times 0.01. All right. Which gives me 0.007. 007 there. All right, 0.99 times 0.7 gives me 0.693. Now I am feeling a little lazy, so I'm just going to go ahead and write down the probabilities as I multiply down. So just to make sure it's really clear, my next calculation is going to be multiplying 0.2 by 0.02. Okay. And those are the probabilities that I found. And you're going to notice a few things about this. These are a couple things that can help keep you on track. First of all, if you come here to the very end and you look within, these two right here, those two, if you add them together, they add up to 0.7, which is this value right here. These two add up to 0.2, which is that value right there. And these two add up to 0.1, which is that right there. This is the relative frequency of all success and supplier outcomes. And so the other thing you'll notice is that if you add up all of these together, it's going to add up to 100%. We just found 100% of all possible outcomes. Okay, so now we've got this breakdown. It looks a little different, but it's almost like a two-way table that's been shown in a different way. Okay, so now what we can do is we can answer this question. What's the probability that your component came from supplier A? If, and I didn't read the full part, because when you try and use this, you find that the connector is defective. So we're trying to find the probability that the supplier was A on condition that it failed. We didn't calculate that yet. We found the probability that it fails on condition that's from A. Now we're doing the opposite. Okay, so now we need to find all of the failures. I have 0.007, 0.004, and 0.004. This represents the entire population of the entire probability, that is, of a failure. So that's going to be 0.004 plus 0.004 plus 0.007. So those are all the possible failure conditions and the probabilities of them. And then what's the probability that it came from A? Well, that's going to be 0.007 is that the failure came from A total. Doing this a little bit backwards, but 0.007 out of 0.015, that will tell us the probability. So it looks like this is going to be about 0.467 probability. All right. We feeling good here? Any questions at this moment? Okay, and just to remind you, as the starting point, we read this to determine, did they give me conditional probabilities or just my kind of marginal probabilities for an event with an and in there? So if it was set up differently, we wouldn't need a two-way or a tree diagram. Okay. This is a question we looked at earlier, but I hid the second part of the question. So now we're going to look at it. Also in the textbook, suppose that 23% of adults smoke cigarettes, 57 get this disease, 57% of smokers get a disease, 13% get a disease. So I kind of want to think through this. You're either a smoker or a non-smoker. We know that 23% are smokers, 77% are not. So what I'm going to pause right here, and I want you guys at home to finish filling out this and see if you can answer that question. I'll give you just a minute or so, and then I'll start filling out the table. Okay, and if you are still working on it, that's fine. I'm just going to fill in this table. And you can see if what you've got matches. And if you use different variables, different names than I do, that's fine. So that's 0.87. So maybe you had that breakdown coming out, and it needs to be numbers like that, but this is the probability of I can't use sick, I'll use ill. Ill, given that it's a smoker, and this is well, given that it's a smoker, and this is ill, given that it's a non-smoker, well, given that it's a non-smoker. So the probability of getting to here will be probability of being a smoker and being ill, given that you're a smoker, which is just 0.23 times 0.57. All right, now just do the same thing for all of these without writing out all of the notation. There it is. That's the, well, that's not our final answer, but that's the breakdown. So what's the probability that a randomly selected 60-year-old has this lung condition? Remember, like I said a minute ago, this, now that we're done, this final level of our tree diagram shows 100% breakdown of all of the possible cases, all the possible outcomes. So I'm really just trying to figure out what's the probability that any 60-year-old has this lung condition. Well, I know that 13% of the population have this disease and they're smokers. 10% have this disease and they're non-smokers. So really it's just going to be 0.1311 plus 0.1001. These are mutually exclusive, so I just need to add these together. There's no overlap. So I get 0.2312 as my probability. All right. Questions there? Were you guys able to get that answer independently? Or at least maybe you're on the way, whether you had time or not? Okay. So I need to briefly talk about Bayes. I wish we could talk about this a lot more. But Bayes' theorem, it looks really complicated. It's not as complicated as it looks. But essentially it does this for us. We can reassess and recalculate probabilities based on new evidence coming in. And I'm going to give you an example of that in just a second. But what's really great about Bayes' theorem is that we can come up with a probability of something happening. And then we have a new piece of information that comes in and says, how does this change the probabilities? So we can just run another Bayes analysis, another Bayes calculation. So it's dynamic and constantly being updated and recalculated. So much of statistics is built on this theorem. And it's funny that we don't really even use it in AP stats, but this is kind of give you a good foundation. And if you guys find that you really like statistics and you want to pursue this further, which I do hope, you know, for some of you that's the case, this is some fascinating stuff here. But let's consider the situation. And there's a video I posted online that goes into greater detail with this situation. So if you want to watch that more. But anyways, a ball is in a bag and it's either red or green, and we don't know which. We place a red ball inside and then we mix them up and we pull one out and it's red. What's the probability that the remaining ball is green? Okay, I'd like to go through this calculation, but I'm not sure if we have the time. In fact, I'll go ahead and say we don't have the time for me to plug this into Bayes' theorem. But we could plug this into Bayes' theorem and we'd find the probability that the remaining ball in there is green is not 50-50 like you might initially think. The probability now is 1 in 3. And maybe a tree diagram helps us here. So that can be done pretty quickly. Right now, we don't know if the ball is red or green. But we put a red ball in. And so now, the only possible outcomes is, if it is red to begin with and we put a red ball in, well, bottom line, I'm going to take too much time to do this. I'd like to talk about it more, but it's really not going to help you in this class too much more. So that's great. We can find this probability using a tree diagram, but if we want to do this over and over and over again, it's really not going to be helpful. So you need to use Bayes' theorem at that point. All right, there are some books on Bayes' theorem. If you guys want to pursue that, you can let me know. So I'm going to put this up here for a minute, and then we'll go through it.
.8.
0.8. There you go. So because we could plug all these numbers in, and we can now look at the probability of B, yeah, divide that 0.4, you get 0.8. All right, now that's not my answer, so that box is just to highlight it. What is the probability of A or B? Okay, so if these were mutually exclusive, I could just add probability of A and probability of B. I know they're not, because the probability of A and B is 0.32. And we already kind of talked about it. You can't have them be independent and mutually exclusive. So they're not mutually exclusive. I need to use the generic, or not generic, the general addition rule. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Luckily, I know all of those. Probability of A is 0.4. Probability of B is 0.8. The probability of A and B is 0.32, which leads me to 0.88 as my answer. All right, so it's kind of a two-step problem there. And if there are questions on any of these, you can stick around after we're done and you can ask those questions. I think I might just run through this one because we have some FRQs that I wanted to spend time with and I don't want to keep us here after our time. So the way I'd approach this, if a package is ordered with rush shipping, it has a 5% chance of being damaged. If it is sent with regular shipping, there's a 3% chance of damage. Only 10% of orders have rushed shipping. What is the probability that the package will have rush shipping or be damaged? Okay, so as I'm reading this, I see this 5% as a conditional probability. This is the probability of being damaged on condition that it's rushed shipping. This 3%, if I read that sentence, it's a probability of being damaged on condition that it's regular shipping, which I can't use R again, so I'll just put N for normal. And the last one is the probability that it was rushed shipping. So knowing that it's conditional probabilities given, I'm going to create a tree diagram. So if 0.1 are rushed, then that means 0.9 are normal shipping. On condition that it's rushed, there's a 0.05% chance, or 0.05 probability, I should say, that it's damaged. So I'll put damaged. 95% probability that it's undamaged. I'll put a U. Right here, when it's normal shipping, 3%, so 0.03 chance under this condition. So damaged on condition of normal, I should put on condition of rushed. And undamaged on condition of being, normal is 0.97. Okay, sorry about that. Now we saw we can just kind of multiply down the line. So it's going to be 0.1 times 0.05, 0.1 times 0.95 to get all these 0.9 times 0.03 and so on. So I'll go ahead and add those numbers in. Sorry. I think that those are all correct. Okay, and this question here is, what's the probability that the package will have rushed shipping or be damaged? So the only case where that's not true is when it's normal shipping and undamaged. So this is the complement of it. I could approach it that way. I could say this is the complement of the probability I'm looking for. Or I could realize that these three right here, that's the probability that I want to add up in order to get it. It doesn't matter because remember, this all adds up to 100% right here. So however you prefer to think of it, adding up all the rushed shipping and the damaged shipping, or just doing the complement of all the stuff that was not rushed and undamaged. And regardless of how you approach it, you should get C as your answer. All right, and that might have been a little confusing. I'm not sure. So are there any questions on stuff we've seen so far?
How did you know this one wasn't or was mutually exclusive?
Like all these are mutually exclusive? Like, are you asking like these final categories, how do we know they're mutually exclusive?
Yeah.
Well, that's a good question because it doesn't actually say anywhere that they're mutually exclusive, but it's just kind of like kind of a thought. You think through it and you realize, is it possible to be simultaneously damaged and undamaged? So we kind of create these distinct categories in our head where there's no overlap. So there's no way it could be damaged and undamaged. Those are mutually exclusive categories. There's no way it could be rushed mail and normal mail. So it doesn't ever say in here that they're mutually exclusive. That is a good question because otherwise we couldn't just add these three up. But because they are mutually exclusive, we can. So it's definitely a good question. If we had, well, this wouldn't work in a tree diagram, but if there was a situation where we had three categories and there was some kind of an overlap between two of the categories or something, then we would have to subtract that overlap away. But again, just hopefully, yeah, you're kind of seeing that these are by definition mutually exclusive. The fact that these probabilities add up to 100% and there's no overlap. So I don't know if that's helpful or not. Does that kind of answer the question?
Yeah, thanks.
Okay. The next question, I think, yeah, it uses the same prompt. I just changed the question a little bit. All right, let me erase this real quick. So luckily, if you were doing the work already, you can kind of follow along. The only thing that's changed is the actual question. What is the probability that a damaged package had rushed shipping? So again, the way we can think through this question, what's the probability that a damaged package had rushed shipping? So we want the probability of rushed shipping given that it's a damaged package. We have the probability that it's a damaged package given that it's rushed shipping, but we want the other way around. So we can just find all of the damaged, all of the categories that fit this condition. They were damaged. So I've got that right here and here. Those are my two outcomes that have damaged shipping, which is if I create my ratio out of this, it's going to be 0.027 plus 0.005. And now it's out of this total population of damaged packages, 0.005 were rush shipping. So that'll give me my answer. And doing that calculation, I get that right there. So I know there's a whole lot to probability, but hopefully it's been kind of building on itself. And, you know, you've been able to kind of build up all these building blocks, you know, to understand the concepts that we're getting into now. I'm not saying it's easy, but hopefully you can follow along and it's making sense for you. Okay, I think that's the last multiple choice. We're going to look at, I got to go through some of these really quick because you're not going to see some of this stuff on the test. But it's worth seeing because there's kind of some general probability and statistics stuff that is worth being aware of. So I'm only going to look at one part of this problem. So when they're using kind of vibrations and reflections off of impervious surfaces, refracting layers, they're trying to figure out the true depth. And in this scenario, there's an actual true depth of 2 feet. But the errors that we get, so when something bounces off and comes back up, and they're using the time to kind of gauge how deep this is, you know, the timing could be off. There could be some other things that throw it off. So there's really kind of an error range. Later, we might call this a confidence interval, where it, you know, it could be plus or minus 1.5 feet as your standard deviation, I should say. So now the question is, if this is only 2 feet down in the ground, then what's the probability that here's your impervious, or your, what are they calling it? Their refracting layer. Here's the actual ground surface. What's the probability that while the average error is 0, what's the probability that you get an error that's in this range right here? All right, because you could have an error range going all this way, but what's the probability that it ends up above ground and you have a negative depth? So the reason I wanted to talk about this is because this is where we can combine stuff we did in chapter 6 with the normal distribution. So really we're using a normal model, and I can almost turn this on the side and say, there's your normal distribution, and a standard deviation is, you know, 1.5 either way. So now we want to figure out a z-score for this. The z-score is, well, 2 feet away, right? 2 feet above is kind of the data point that I want to find the z-score for. And the mean is 0, the standard deviation is 1.5. So if I do that, I end up with 1.33. And this tells me that at a z-score of 1.3, I'm going to be moving into this above ground negative depth range. And so what's the probability of falling into that? Well, I can use normal CDF. And this is where we're going to tie in normal distributions with probability a little bit. So if I run a normal CDF and I go from 1.33 up to the higher end of that range, then there's a 90, so probability of a negative answer is 0.0912. And I'm going to stop right here, but I just wanted to show you that this area under the curve is the probability of falling into that range. And now I can use that in a probability calculation. So, you know, I could do that. I could answer the next question using that probability. Okay, so in the next one, we have 3 independent depth measurements. What's the probability that at least one will be negative? We had a lot of these at least one problems, but I'm going to skip this one for now. If you want to hang out after class, we can go over it, but there we go. Trying to pause just a little bit to let you guys breathe and find out if you have any questions. Okay, the next one. Again, we're not going to go through the full problem. Well, we might. We'll just see the time. So we've got 2 dies. One of them is die A has 4 9s and 2 0s. Die B has 4 3s and 2 11s. Anytime you roll, the higher number gets the win. So if you're playing this, which one are you going to want to pick? And does anyone have any initial thoughts on which one you'd want to pick? Does one of them seem like it's more likely to win than the other? Okay. I think either everyone has wandered away from their computer right now, and I'm talking to myself, or no one is wanting to venture a guess for fear of looking like an idiot. All right. So let's set this up. I'm going to have die A on the left. Here's the way that I approach it. I want to figure out all the outcomes. When there's only 36 outcomes, it's not that big of a deal. Okay, so I should have moved this a little bit, but die A has 2 zeros and 4 nines. I'm going to put them in order. So 0, 0, 9, 9, 9, 9. Die B has 4 threes and 2 11s. So 3, 3, 3, 3, 11, 11. So now I want to figure out any possible combination of rolls, who wins. And I'm going to figure out how many times does A win. Well, anytime A rolls a 0, it loses. Loss. Anytime B rolls an 11, A loses. Anytime A rolls a 9 and B rolls a 3, A wins. So here we go. We got our victories. There it is. Those are all the possible outcomes of rolling these two dice. So if we look at it, A wins. The probability of A winning is going to be 16 out of 36 outcomes. The probability of B winning is going to be, well, that would have to be the complement. So that'd be 20 out of 36 outcomes. So it looks like die B is actually the better one. And that might not have been where you were leaning. So anyways, the next question is a little bit weird, but I think we can figure this out. We know the probability that A is going to win. So if player A receives 45 tokens every time he or she wins the game, how many tokens must player B, or must the other player receive for using die B in order to make this a fair game? And it's a fair game if in the long run you get the same number of tokens. So basically want to see what the reward for A is. So I'll put the reward R for A times the probability of A. And these have to be equal. The reward for B times the probability of B must be equal to the reward for A times the probability of A. I'm not going to have a question like this on the test, but I think it's just good for probabilistic statistical thinking, okay? The reward for B has to be, or times the probability of B. These two have to be equivalent. Okay, and in some ways this is going into the next chapter, but it's worth it kind of getting a head start. So the reward for, let's see, for die A receives 45. So they get 45 tokens, and the probability of this happening is 16 out of 36. We don't know the reward for B, but we know that this happens 20 out of 36 times. So now it's just an algebra problem. We divide the left side by 20 over 36, and when we do that, I believe the reward for B is just going to be 36. Of course, you guys can double check me. So 45 times 16 divided by 36, all that fun stuff. And there you go. Again, you won't see anything like that on the test, but it is, I think it's just good to stretch your brain a little bit. This is something that this would be a fair question to ask on the test. The last one is the hardest part. What we've got is this test. It's called ELISA. I don't know what it stands for, but it is testing for HIV, and what it does is it measures levels of antibodies in the blood that should be elevated if HIV is present. But there's a natural sort of variation in human the quantities of this, so it's not always correct. So here's what happens with this. They want to, there are some people getting trained on how to do this, and they drew 500 samples. 500 of these are known to contain HIV. 500 are known to not contain HIV. And it gives you the breakdown of how many were positive and negative. This is a good way, this is gonna be a two-way table. So HIV, yes or no, and then test. Was it positive or negative? Of course, we got our totals. There we are. So we had 500 with HIV, 500 without. Among those with HIV, 489 tested positive, 11 tested negative. Among the 500 to not contain HIV, 37 tested positive and 463 tested negative. And then we can now add up across the rows, and that should be 526 and 474. This adds up to 1,000 total samples. Okay, so we got our two-way table. When a new blood sample arrives at the lab, it will be tested to determine whether HIV is present. Using the data from the training program, estimate the probability that the ELISA would be positive when it is applied to a blood sample that does not contain HIV. So we want to know the probability that it's going to be positive on condition that it does not have HIV. So if I look here, here's my condition, no HIV, but positive is 37 out of 500. So there's my probability. And I'll go ahead and create a decimal for that, which will be helpful in a little bit. So 0.074. Okay, now that first question really isn't too bad. Setting up the two-way table might have taken a little bit of time, but if you got 15 minutes to do this, you know, you could set that up in about 5 minutes, and yeah, that's no problem. Take another minute to do that. Okay, among the blood samples examined in the training program that provided positive ELISA results for HIV, what proportion actually contained HIV? So now I'm looking for the probability that it did have HIV on condition that it was positive. So now that's going to be 489 out of the 526. Again, really not so bad with this problem. Maybe you took half your time going through and calculating, you know, the first two answers. So now you got, you know, another 7 minutes to consider this last part of the question. And this is the one that, yeah, it's a tricky one here. So we have to take a second to wrap our heads around this. When a blood sample yields a positive ELISA result, 2 more ELISAs are performed on the same blood sample. If at least one of the 2 additional ELISAs is positive, the blood sample is subjected to a more expensive and more accurate test to make a definitive determination of whether HIV is present in the sample. Repeated ELISAs on the same sample are generally assumed to be independent. under the assumption of independence, what is the probability that a new blood sample that comes into the lab will be subjected to the more expensive test if that sample does not contain HIV? Wow. Try and wrap your head around that one for a minute. Okay, now this is definitely the kind of question, and I know that you probably would want to spend about 5 minutes just staring at it, but we have 15 minutes in class, and I don't want to hold you over. So I'm just going to kind of run through this, and I should tell you now, there are some practice problems on the Canvas page. Of course, you have homework tonight, and I'll show you that in a second, but when you go to the today's class page, so September 21st class, there's a PDF with extra practice. It has some FRQs, so I encourage you to look through it. All right, but let's look at this now. I'm going to kind of diagram what happens. So I've got a blood sample, and it came into the lab. And according to this sample does not contain HIV. So I'm going to say that this is no HIV. I'm just going to put that next to it. So here's what happens right away. You can almost do a tree diagram for this. It either gets a negative result or it gets a positive result. If it's a negative result, it's done. And 87, whatever we came up with, I actually don't remember what percent, 87% or something like that of the, whatever the case, it doesn't matter. If it goes over here, we're done, right? We're not talking about that scenario. We're talking about this case. So it does not have HIV, and yet it does get a positive result. So that doesn't mean that there's HIV. In fact, we know there's not. What happens next is you move on, and now you have to take 2 releases. And then if either one of these is a positive result, then you move on to this more expensive test. So I'll just put test 2. And that's kind of the scenario that we're talking about. So what is the probability that a sample without HIV makes it through this whole process? It tests positive, and then it tests positive 2 more times, and then it has to make it there. Okay, so if we're able to visualize it, that's part of the process. Okay, and I might have to erase all this work down here so that we can diagram out exactly what our probability calculation is going to be. All right, oops. All right, again, not the simplest calculation, but we can do this. So the probability that, first of all, it comes in and it gets a positive test. So we need to find the probability that we get positive on condition that it doesn't have HIV. All right, and that just happens. But then after that, and we need to, well, here's where we get this. Where is it in here? At least one. That phrase should jump out at you. At least one. If it's this, then we kind of need to consider the complement of failure rather than the success. So the failure of this would be if we get negative 2 times. So I need to get the probability of negative given that there's no HIV, and negative on the condition that there's no HIV, and the complement of that. So just to make sure this is really clear what we're talking about, if I get a negative test and a negative test, it stops right there. No more testing is done. If I get a negative and a positive and a negative, or a positive and a positive, then I have to keep moving forward. So the easiest way to calculate that is to figure out the complement of getting a negative and a negative. And we talked about that, but now we're kind of combining this with other calculations. So does this make sense? This is where it can screw with your brain a little bit. Okay, so luckily we can figure out all these. In fact, we already know the probability of positive given that there's no HIV is 0.074. Because these are independent, I can just multiply these. And, well, except this is going to be a complement, so it's going to be 1 minus the probability of, well, what's the probability of negative given that there's no HIV? So that's going to be 463 out of 500. .926. So that's the number I was reaching for earlier and I couldn't remember. So there's a 93% chance that we're going to get a negative result. And there's a 93% chance we're going to get that a second time. So once I multiply those together, that's the probability of getting 2 negative results. But of course, anything besides that, so it's going to be 1 minus, and that's going to be the probability that at least one of them is positive. And that is the actual calculation we need to do. So now it's going to be 0.074 times 1 minus 0.926 times 0.926 and it looks like there's a 1% chance that under this scenario, we're going to end up with someone without HIV having to take a more expensive test. Okay, now, maybe it's looking at the screen all day. Maybe it's trying to explain this. Maybe it's trying to think through it. My head is kind of hurting now. But that can happen, right? Looking at these problems, they can really mess with your brain. So anyways, that is this particular FRQ. We've worked our way through it. And I'm going to leave that up because I'll go back here in a second in case people want to look at that more. But I just wanted to point out, you have your homework. You have that extra practice, which does not need to be turned in. It's just a PDF on the class page for today. And the unit test is tomorrow. If you have a lot of questions, come in with problems, especially ones from the textbook, and we can look at those before you decide to do your test. So, all in all, hope you guys are feeling decent with this stuff and practice a lot tonight. Come in with questions if you have them, and I'll see you tomorrow. Good luck.
Bye, Mr. Davis. Have a good day.